Hello everybody. In this video I'm going to be solving some problems from my university's list of, um, I guess I should say, a test bank for their um, sort of final examination for a master's degree. So the way my university does it is that the test is split into three sections, one on abstract algebra, one on analysis, and one on topology. So today I'll be solving some problems from the algebra test bank, and specifically they have it split up into more subsections, so these will all be group theory problems. So let's get into it. So this first problem says, let H be a normal subgroup of G and K be a subgroup of H. So first we want to give an example of the situation where K is not a normal subgroup of G. And so obviously there are many possible ways to give a scenario, right? But really the easiest way to do this is that you can say let H equal G, right? Because G is always going to be a normal subgroup of G, right? Sort of in a trivial sense. And I don't know if this would, if this sort of like trivial example would get you marked off points on the exam, but it's one way to go about it if you can't think of another example. And then you simply have to find a scenario where K is not a normal subgroup, right? So of course for this to happen, we would need G to be not abelian. Okay, my program is like flashing for some reason. We would need G to be not abelian, right? Because if G is abelian, then every subgroup is going to be normal. So for our example, we would have to pick G not abelian. And so some of the best examples of non-abelian groups to have in your, I guess, memory, right, to pull for examples is going to be a permutation group. And we can pick the permutation group on 4 symbols. And then, right, so we're going to let H be S4 as well. And then for a non-normal subgroup, we can pick the permutation group on 3 symbols, right? And so, and so let's say we're defining this in such a way that the elements of an S4 are acting on, let's say 1, 2, 3, and 4, right? Then K would be the subgroup of elements which fix the element 4. And essentially, we can see that this is not normal because you can conjugate by an element and you'll have 4 going somewhere else, right? So let's say, for example, we applied an element of K and we permuted, let's just say 3 and 1. So 3, 2, 1, 4. Or actually, hold on. So first we would want to apply something in S4. So let's say we just cycle to the right, and then we apply a permutation. So on the first 3 elements, so that would give us 2, 1, 4, 3, and then we apply the inverse. So we cycle to the left, and that's going to give us 1, 4, 3, 2, right? So this total permutation, as we can see, did not fix 4, so this is not a part of our subgroup, right? So this is showing explicitly that K is not a normal subgroup of S4. And for part B, we want to show that if H is cyclic, then K is in fact normal, right? So, right, so we have, if H is cyclic, let's write H is going to be generated by A, some element A, right? So let's write this out as E is going to be our identity element, so this is going to be our identity. That's a standard notation. Some people like 1, but I prefer E for just group theory. And then A to the n, right? So this is going to be an let's do A to the n minus 1, so we can have the order of A is n, right? Then K K is going to consist of essentially some subset of this containing E, and it's all going to be powers of A, right? And of course, this has to be defined in such a way that these exponents are going to form some abelian group under addition. And so this is going to be an abelian group as well. Basically, the thing to notice is that if H is normal, right, then for any G in G, G inverse is going to be an H. So this implies that G inverse is going to be a power of A, which we can say, let's say, A to the K sub G, right? So we can sort of define a map from G to this exponent. But then, if we take any element, x in K will be x equals A to the J, right? And therefore, if we conjugate by our group element, conjugation preserves exponents, right? Because if you think about this, you could sort of prove by induction that these inner things will cancel out, and then the A's will group up and multiply together, but you'll always have the G on the left and the G inverse on the right, right? And this is G inverse is A to the KG, and this is to the J power, and then this is going to be A to the J to the KG power. So this is some product of, this is X to the KG, and so this is going to be in K. And therefore K is normal, because if we conjugate by any group element G, then we get an element of K. Our next problem is going to be proving that every finite group of order at least 3 has a non-trivial automorphism. And this seems like a sort of simple, I mean, obviously it's one line, right? So this seems like something simple to prove. It also seems like something very important to know, right? Because, automorphisms are very useful, say, in Galois theory, and so it's nice to know that you have these non-trivial automorphisms. and it's good to know that they exist, at least non-trivially, right? But it turns out to be not that easy to prove, right? So the way we will approach this is split this up into different cases. So first, let's say G is not abelian. Sorry, let me say case 1 will be G is not abelian. And so in this case, we can then there exists some group element such that the inner automorphism which sends a group element G to the conjugation of G with X is non-trivial. Right? Because if I pick some or essentially this means that there has to be some pair of elements where gx is not equal to xg, right? Because G is not abelian. If G was abelian, then this would always be true. But if it's not abelian, that means that this is true for some X and G. So we just have to pick one of those group elements to define our inner automorphism on, right? So, and this is for some specific G, I should say. It doesn't have to be this doesn't have to be not true for every G, just for one specific G prime. So that's the first case. The second case is that G is abelian and there is an element X in G, X in G, such that X squared is not equal to the identity element. And so for this case, what we have to do is say that then the automorphism then G sending to G inverse is a non-trivial automorphism. Now, it's important to notice that this map is not an automorphism when G is not abelian, right? Because AB is sent to AB inverse, which formally is B inverse A inverse, right? So this is only an automorphism when G is abelian. So I'll just set that off to the side. And so this, and it's non-trivial because there's going to be some, because X will not equal X inverse, right? So this is why it's non-trivial. This specific X that we are assuming exists in our group. Then our third case is G is abelian, and G squared equals E for all G in G. And so in this case, now essentially abelian groups, sorry if I just blew into the mic there, there's a hair on my face. Abelian groups are the same thing as a module over the integers, right? And a module is like a vector space, except you're working over a ring instead of a field, right? Or just, it's a more general structure than a vector space because you're working with a ring that may or may not be a field, right? And this is because you can write things additively, essentially n1g1 plus dot 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 plus nkgk, right? Where the n sub I is in these are integers, and g sub I are the group elements. And I should say this is finite, at least you can write it like this if it's finite. And if every group element, though, satisfies g squared equals E, right, in the sense of if we're writing it additively, that means that 2g equals 0, right? Because in the additive notation, E equals 0, and exponents become multiplication by integers. So what this means is that we're actually working over z mod 2, right? Which I will write as z mod 2z because that's the more common notation. Right? We actually have a z mod 2z module because every time we have 2 of some element, it becomes 0. So it's like we're modding out by 2, right? But z mod 2 is a field. So this structure is actually G is a vector space, a finite dimensional vector space because G is finite dimensional. G is a finite dimensional vector space. And what this allows us to say is that G has some basis. Let's say V1 through Vn. And there is a group automorphism achieved by swapping let's say V1 and V2, right? You can swap any two of the basis elements, and this is actually going to define an automorphism on the group because it doesn't matter what the basis is, right? Obviously the vector space structure is going to stay the same, but this permutation is going to swap around the group elements, but in such a way that the structure of the group actually stays the same. So this is actually a what was seemingly a very important result. I mean, it is an important result, but it seems so simple, but you have to actually break it into these cases, and then at the end, you have to bring out this more advanced structure. So it's actually a very interesting problem that you should be aware of if you're a student of abstract algebra. And the last problem for today, sorry, there's like this bit cut off that's for the next, like the G4, right? The next problem is regarding the structure theorem for finitely generated abelian groups. So the first part is to state this. I'm not going to write it out because obviously if you're watching this video, that means you have internet access and you could just Google this. But in a sense, what this is saying is that if G is a finitely generated abelian group, then G is isomorphic to a direct sum of a certain amount of terms. So let me write this out nicely. Plus dot dot plus z mod qn z, where n is the rank of G, and if G is a finite group, then n is 0, and Q1 through Qn are prime powers. Now B says if P and Q are distinct primes, determine the number of non-isomorphic abelian groups of order P cubed Q to the fourth, right? And essentially, knowing this structure theorem, we know that G is going to be isomorphic. G is a finite group, right? So we don't have to worry about this first term with the infinite cyclic group, Z. And so, what should I say here? We know we're going to have some number of terms involving powers of P, and then some number of terms involving powers of Q. And now I should mention here that in the finite dimensional case, so I should say here, if n equals 0, then G is a finite group and the order of G is equal to the product of Q1 through Qn, right? So for B, right, we're going to have terms involving powers of P and terms involving powers of Q, and they have to add up to having P cubed and Q to the fourth. So essentially we just have to count up the partitions of 3 and the partitions of 4, right? And by partitions I mean the ways you can, the unique ways you can write these as the sum of natural numbers. So for 3, you only have 3 ways. You could have 3, 2 plus 1, or 1 plus 1 plus 1. For 4, you have 5 ways. You could write 4, you could write 3 plus 1, you could write 2 plus 2, then you could write 2 plus 1 plus 1, and then you could write 1 plus 1 plus 1 plus 1. So this gives us 3, and this gives us 5, and these are independent of each other, right, because we're dealing with separate primes. And so the number of groups is 3 times 5, which is 15. And that's it for this video. Hopefully you like this content. I'm going to be making another video on topology problems today, and that will probably be released like a day or two after this video comes out. So if you like this content, let me know if you want more videos like this, and I'll see you in the next video.